some consulting work on American
feeling in the room was
Don't ever say to her that
What about the Chautauqua Institute?
Introductory discussion on the ethical
We left
more of a community.
before China took back over.
Currently doing in autism.
It's no secret that Earth's climate is changing. What's not so clear is how fast or what exactly we can do about it. We talked with Richard Alley, one of the world's leading experts on climate change and a scientist who really walks the talk. Richard Alley is an Evan Pugh Professor of Geosciences at Penn State and was elected to the National Academy of Sciences in 2008. He was a member of the Intergovernmental Panel on Climate Change that shared the 2007 Nobel Peace Prize with former Vice President Al Gore. His research on ice sheets in Antarctica and Greenland revealed secrets about past climate change and shed light on what the future might hold. Among his students, he is perhaps best known for his unorthodox teaching styles, including his use of music videos to teach scientific concepts in an entertaining and memorable way. Here's our conversation with Richard Alley. Richard Alley, welcome to the conversation.
Patty, it's a pleasure to be here.
You're one of the world's leading climate researchers, and I think it's always interesting to know, did you choose climate research or did it choose you?
Oh, it chose me. I loved collecting rocks in high school. I wanted to be a geologist, and the ice guy at Ohio State had a summer job. And then I got into glaciers and ice sheets, and climate change came out of that.
So the ice guy, and you've spent a lot of time on the ice. In fact, you spent 5 field seasons in Greenland and 3 in Antarctica. Describe these research expeditions.
I've worked on the edges, looking at the geology and the record of the ice, how it's expanded and contracted, and then I've lived up in the middle. And the middle of the ice sheets is, you're 2 miles up and the ice is 2 miles thick, and the hottest day in summer doesn't get up to the point of melting, and it's snow. And that's it.
Yeah, we're talking about a place that in some parts of Greenland, for example, there is, the sun doesn't rise for 3 months. We're talking about a cold and a dark climate. What is a field season? How long are you there? And what does your research entail day to day? What's a typical day?
Yeah. So I've been a lightweight. I've never gone for more than 6 weeks at a time. So, and we go when it's sunny, so that's fine. The times we were working in the middle on ice cores, a lot of it we worked actually down in a snow cave to stay out of the wind and the sun. And you just dig this giant hole in the snow and you put a roof on it. And we had a complete laboratory down there, and we were working on the physical properties, the appearance and other things of the ice core. And so you take this cylinder of ice, it's about that long and about that big around, and we make measurements on it and look at it, describe it, photograph it, and then roll it to the next person, and another one come in, and we do it over again, and we did that through 2 miles of ice.
2 miles. 2 miles of ice. How do you extract 2 miles of ice? And we're talking about a vertical extraction.
With a big drill. So they've got a drill that would be like a pipe, and there's a hole in the bottom as well as the top. And it's just like drilling a hole in the door to make a hole for the doorknob, except instead of drilling through something that's deep, we actually took about 6-meter pieces at a time, and then we wump those into 1-meter pieces. So you're looking at 20-foot long chunk that would come out, and then you go down and get another one, and go down and get another one, and go down and get another one, and that was 5 years.
5 years to drill 2 miles.
Oh, yes.
How can a history of climate be reconstructed from an ice core? What makes ice such a great record keeper?
Yeah. If it's in the air, it ends up in the ice. Where we worked in central Greenland, where we're working now in West Antarctica, summer, winter, you can see them, you can measure them chemically, electrically, and other ways. And so we actually did a lot of work on saying, yes, this is summer, this is winter, this is summer, this is winter. Then you better check it. So we know, for example, in 1954, we blew up an island in the Pacific with an atomic bomb, and the fallout from that is around the world. And you can find that fallout in the ice. It came in 1955, so we can count down to 1955, say this had better be hot, you look for how hot it is, and we got it right. And then we know in 1783, Ben Franklin is in Paris representing the young United States. he sees these dry blue fogs blowing across, and he says there must be a big volcano somewhere. Well, the people in Iceland knew what they were having a terrible time because Loki was erupting and it was putting fluorine on the fields and the sheep were dying, and pieces of Loki end up in Greenland. And if we count down to 1783, we had better find pieces of the volcano with the right chemical composition sitting there. And so all the way through written history, we can check. We can actually say, this is Vesuvius and Elgin, Hekla and Katla and Loki and so on. And so we know it works.
You're talking about being able to identify things to the year. Can you go to the month or the week or the day by looking at ice? I mean, how exact is it?
It's harder to go to shorter times because it's really easy that summer and winter are different, but March and April, there isn't anything that says, hi, I'm March. And so you can sort of say this is summer and this is winter, but it's hard to pick out individual months.
So, and you went down 2 months. I'm just curious. Was that an arbitrary amount? Was that what the technology would allow you to go to? And could you have learned more if you had gone 3 miles deep?
Yeah, 2 miles and you hit rock. So the pile is about 2 miles thick, and so below that, had we drilled a little bit into the bed about yay far, and it's a chunk of granite. So.
You have determined from looking at these ice cores that the climate changes have ranged from the slow and gradual to the fast and dramatic. In fact, abrupt climate change. How abrupt?
We've seen changes that are sort of northern Alabama to southern Maine in 10 years.
10 years. And
sort of 10, maybe
okay.
20, maybe 3, but that order, yes.
And the theory is if climate change has been abrupt in the past, that there's every reason to believe that it could be abrupt in the future.
It surely might be. If you look at the history, we see most of the time the climate's well behaved. It's changing slowly, it's changing gradually, we understand what's going on, and just occasionally you get these big jumps. So over the last 100,000 years in Greenland, there's 20-odd really big jumps. And so if you look at the future, and you see sort of our projections, what we expect, what you'll see is some smooth curve running into the future. That's the best. That's what we can hope for, is that the change will come smoothly. Sometimes it came smoothly in the past, sometimes it came abruptly and surprisingly. And the more surprised you are, the less ready you are for it, the harder it is to deal with.
In fact, you've written a number of papers and you've talked before members of the U.S. Senate about inevitable surprises.
It is indeed so, because we know that surprises are out there, and it's a surprise. If it happens, you're surprised. If it doesn't happen, you're surprised. And so there is some element of predicting the climate. We're going to get better and better and better, and we're never going to be perfect.
In terms of our knowledge about the climate, where does the ice core research that you're doing meet with the work that oceanographers are doing, the work that mathematical modelers are doing? How does it all come together?
It really is coming together. And in the time that I've gone from being a student to getting gray, we really have gotten to having a science of climate change and an ability to demonstrate skill. People have actually been running these models long enough that they can say what we told you 15 years ago is happening. And the models really do work in reproducing things that happened in the past without cheating. And they really have worked in simulating things that are happening now without cheating. And so it's an art part of it. If it happened, it must be possible. If you see that it changed in the past, that better be something that you understand and you put in your model. And if we know what happened in the past, you can take your model and test it against what happened. So if you're doing climate is a 30-year average. We've only been doing this for 30 or 40 years. And so we only have a very small number of tests over recent decades. If you wanted to be a weather forecaster, you can find out how good you are every day. And in the time you're a student here at Penn State, you can do thousands of tests to see how good you are. If you want to be a climate forecaster, where do you find many, many, many different times and ways to test yourself to see if it works? We'll build you a past. We'll show you what happened. You take what you know about the sun and the orbits and the CO2 and so on and see if your model simulates what really happened. And they do.
Now, in this history of climate that you've been able to establish through ice cores and other means, Do we know why there was this abrupt climate change that you've described?
Right. So the big jumps in the North Atlantic ultimately are linked to whether the ocean freezes in the winter or not. If you go to somewhere north of Alaska, the ocean freezes in the winter, and Alaska being downwind in winter, it's really cold. If you go to the same sort of latitude off of Norway, the ocean is open in the winter, and Norway doesn't get that cold in the winter. If you put a little more fresh water in the surface ocean, off of Norway will freeze in the winter, and then it gets really cold in the winter. And the difference between about freezing and North Dakota sort of difference in winter time. What also happens is when you freeze the North Atlantic in the winter, it changes things downwind. And in particular, every time in the past that it's been really cold in the North Atlantic in the winter, it's been dry in places in the monsoon belt where a few billion people live now.
So what you're really sort of describing is this climate system that relies on the sun and the oceans and the atmosphere and land masses and all of these things and how they interplay with one another. So I'm wondering, how do the parts of our climate system interact, and when, as you describe it, when is there a tipping point, and what causes a tipping point?
Right. So the interactions are just all over. People have studied the climate, for centuries. And we got really serious about the climate probably in the 1970s, to be honest. And at that point, particles are blocking the sun and they're making cooling. There might be an ice age in 100,000 years. CO2 is causing warming. And the government asked the National Academy of Sciences, they said, okay, what's coming? And the National Academy of Sciences says, probably warming. But we're not sure. You need climate science. You need to put serious investment into this and figure it out. And it sort of took 30 years from that to figure out how everything fit together, to put the pieces in place, to test them and to understand it. And what you get to eventually is an understanding that works. We sort of know all the big pieces in the story well, not perfectly, but well. And what we find is that indeed, typically the climate is well behaved. You turn up the sun, it gets warmer. You turn up CO2, it gets warmer. Various other things, there's sort of some big knobs and some fine-tuning knobs. And then we find that there are these times and places that something weird can happen. If it gets a little drier, the plants quit pulling water out of the soil to make rain that waters the plants. The water goes down the creek, it's not going back up, and then it gets drier yet, and the plants die, and then you've had something has changed in a hurry. Or a little more fresh water, and the North Atlantic freezes in the winter, and the monsoon sucks in cold air, and it quits raining at times in places where a lot of people live. And the analogy is this business of, if you're leaning in the canoe, you can lean a little bit, you can lean a little bit more, and then at some point you lean a little too much and it flips over. And there are those thresholds in the system. We may miss them. You can do the whole canoe trip and never flip it, but you can flip it.
In fact, you even compare this to driving. You can drive along, and if you drive enough, you will encounter some difficulties, and there is the possibility that you'll be run over by a truck. But that being the case, how do you behave knowing that it's a possibility?
Yeah, well, we paid extra for the side airbags on the car, so and we made sure, and we've got driver training, and so one of the ways that we behave is we take out insurance against the possibility of the disaster, and we clearly have insurance on the car. We clearly have design of the car. If you were to ask how much of that car is linked to safety. What do we pay for the airbags and the seat belts and the crumple zones and all the things in it? We put a serious amount of the value of the car into protecting ourselves from things that very well may never happen.
Now, you published your findings from Greenland and from Antarctica in an award-winning book, The 2-Mile Time Machine. That book was named the National Phi Beta Kappa Science Award winner for 2001, and it's been described as this brilliant combination of scientific thriller and memoir and environmental science. And while all scientists won't agree with the conclusions you come to in that book, most people agree that your tone is measured, that you're not an alarmist. And in fact, some people who listen to you and to others say, are we're surprised a bit by your optimism, and I'm wondering maybe optimism is not the right word, but I'm wondering if it is, what indeed is the source of that optimism about solving this problem?
Well, thing one is I work with students, and it's hard to be really depressed all the time when you see how bright people are. Okay, so thing two is that if you're a historian of people, I'm not a historian of people, but I read this. If we look back, we can see lots of times and lots of places where people have failed miserably, where the climate changed, where the society changed, where the challenges changed, and they failed, and their society collapsed. And you can go read Jared Diamond's book on collapse, and we know all these terrible places where they failed, and people starved, and they died, and they had wars and disasters. And there's more of us, and there's more of us living better now than ever before. Which means usually when we are challenged, we win. We figure it out. We solve the problem. We meet the challenge. We move ahead to something that's better. And often enough, we fail to remind us that this is not a given, that you really do have to work hard and you really do have to be smart and maybe a little bit lucky.
But sometimes the American mentality, this can-do attitude is that we can wait until the last minute and sort of in cavalry fashion run in and save the day at the last minute. And I don't know if that's going to work this way when it comes to global climate change.
I'm gray enough, I can remember President Nixon declaring war on cancer. And, you know, sort of, if we can put a man on the moon, we can cure cancer. And it sort of took 30 years to make much of a dent in that. And we have not cured cancer, but some cancers we've cured. We've made a huge amount of progress. But it really took 30 years of hard work to figure out how to move ahead, because that's a hard problem. Global warming, new energy sources are a hard problem. We are not going to flip a switch and have it solved. This is a 30-year issue.
You talked earlier about scientists like yourself going to the government and saying we need to research this, we need to understand climate. And in fact, the United States has spent more on climate change research than any other country. But in terms of, we know a lot about it, we've invested a lot of money in it, but how much have we done?
Yeah, well, clearly the understanding of climate has been great. And we've gotten to the point of knowing with confidence that if we continue business as usual, burning lots of fossil fuels, that when you look ahead 2, 3, 4 generations, we will have made life harder for a whole lot of people because of the changes in the climate, and we will have made life harder for a whole lot of ecosystems because of that. And that result is about as good as science gets. It's a very solid thing. We clearly have, if you walk across campus here, you'll find the people who are trying to figure out how to take the CO2 that we produce from the coal and put it back in the ground. You'll find the people trying to figure out how you can make fuel not just by burning food, but by burning the things we can't eat. You will find people who are working on solar cells. You will find people working on a whole bunch of things that are part of the answer. So clearly, we are looking into the solutions. The history, though, is published by Andy Revkin in the New York Times. From the peak of the U.S. interest in solving energy problems back after the oil embargo, we cut our research in half. That was the public research, and private industry responded by cutting it by way more than that. And so this has not been the top. We've been working harder on things such as cancer. This has not been the top of the list for a very long time. A lot of people who are looking at it now are saying that it should be very much higher on the list.
In 2004, a disaster film came out. It was called The Day After Tomorrow, and lots of people saw it. And in this film, there are snowstorms in New Delhi. There's tornadoes destroying Los Angeles. Scotland is flash frozen. New York is drowned in a tidal wave. And still, the U.S. government fails to act. Now, of course, this is fiction. But in a real case scenario, what kinds of things, if we don't take care of business. What do you envision?
Right. So the sort of the central estimate, we end up with the dry zones that come into the southwestern U.S., that come into the Sahara and other places. So the dry zones in the tropical circulation get bigger and drier. The grain belts tend to get dry during the summers in a lot of places where we grow a lot of our food. We tend to end up with more droughts and more floods. That seems contradictory at first, but there's more water up there, so when it rains, it comes down really fast, and then it evaporates pretty fast. Right now in April, the whole winter, the tomato patch has been damp. And in the summer, we'll have a flash flood on it from some giant thunderstorm, and the hail will beat down the tomatoes. And then 2 weeks later, it's dry, and I got to go out and water it. So you get more droughts and more floods in the warmer time. There's a lot of uncertainty on big storms, but there's more energy to drive hurricanes. We're not sure whether they'll spin up more, but the ones that get started may get stronger. Tropical diseases are controlled by a lot more than just temperature, but right now some diseases are held at bay because they freeze to death in the winter, and if we don't freeze them, they have a chance to expand. Sea level rise is very, very hard to avoid, and so what you look at is sort of warmer in a lot of places, sea level rise in a lot of places, and pushes on us in many ways. Need for rare and endangered species to migrate. We put them in wonderful preserves and national parks and little islands, and then the climate changes and they need to move, and we're in the way, and how do they get there? So those are some of the things that come out. For a small warming, if you've got winter, bulldozers, and air conditioners, it doesn't cost you much, because a winter closes down the airport, that's costly. And if there's fewer blizzards, that helps. If you got an air conditioner, you work in the summer, you got a bulldozer, you can build a wall against sea level rise. If you're a poor person and you don't have winter and bulldozers and air conditioning, warming doesn't do you any good. It's just bad all the way around. So initially, we're not being hurt very much. Poor people in hot places and anyone trying to live a traditional lifestyle are hurt in the short term. In the long term, as you look out decades to centuries, then the damage spreads to everybody.
And of course, in the United States, where we're 5% of the world population and contributing 22% or a little bit more of emissions, we have a greater responsibility.
It is certainly clear that I am not allowed to do my business in your yard. I'm supposed to use a toilet, but I am allowed to blow my CO2 over your country and change your climate.
Now, I mentioned a moment ago the day after tomorrow, and to a certain extent that may help to explain these annual Gallup polls that show while most Americans do believe in global warming, a growing number of Americans believe that the threat is exaggerated. In fact, 41% believe that the media is exaggerating, and that's a 6-point jump from just last year. Global warming ranks number 8 in terms of environmental concerns, and concern over contamination or pollution in drinking water turns out to be number 1. How big a problem is it to communicate to the American public, or to get politicians and the media and scientists on the same page about the threat? Yeah,
it's a huge one, and it's a problem in the same way that infrastructure is a problem. Our bridges are rusting. We need to fix the bridge, but you drove over it, and until somebody breaks and falls through, it's hard to get traction on that. We are not tremendous at worrying about things that are well off in the future. And for us in the United States, most of the damage from global warming is well in the future. And so it's a difficult thing to say.
How far into the future?
It's depends on what you worry about. If you're worried about rare and endangered species, we're already getting to the point that they're in trouble. If you're worried about the global economy, we may have some decades, may have some degrees before it really shows up as a major impact. If you're worried about the poor people who are not as important economically, but who sort of have lives of their own, then the problem comes sooner. So the last time this was done, the United Nations, the IPCC, asked the experts, how much warming until you get scared? And some of the experts said a little bit, and some said more, and then they said, but you have to tell us what we're being scared about. And so they sort of said, if you're worried about rare and endangered species, a couple degrees, most of the experts are really nervous. If you're worried about poor people in hot places, another degree and the experts get nervous. If you're worried about the global economy, another degree or two before they really get nervous. And so then it's how long to get that many degrees. It depends on how fast we burn.
And the IPCC, the Intergovernmental Panel on Climate Change, is talking 3 to 7 degrees in the next, 50 years?
Yeah, depending on the scenario. So clearly, there are uncertainties about the future from what we don't know about nature. And there are uncertainties about the future from what we don't know about what humans will do. And right now, probably the biggest uncertainties are based on what we do, not what we don't know about nature.
You mentioned the Intergovernmental Panel on Climate Change, the IPCC. You're involved with that organization. Tell us a little bit about what it is and what your involvement is.
Right, so this is, governments of the world, the people of the world have always had this problem with science because we as scientists, our job description says argue. Our job description says if you're going to ask the world to rely on your science, you have to demonstrate that it's really, really good. And demonstrating this means trying to break it. You know, you take ideas and you subject them to everything you can think of to see if they break. And if they stand up to all of that, then they're really good. And so, you know, physicists can say, is this really right? Is there a better theory of this? Is there a... And so all the time we argue. And you lift the lid and look in, and what do you see is us sitting in there arguing, and you say, how in heaven's name do I make sense out of this? And those of us arguing have a pretty good idea what's solid, what's speculative, what's just silly, but if you're not paying attention closely, you don't. And so the governments have built what they call assessment mechanisms. In the United States, this started with Abe Lincoln and the Civil War, and he wanted advice on munitions and things like this, and Congress founded the National Academy of Sciences. And what they do is you get a whole bunch of good scientists, you get the full range of views, you get some graybeards and some young upstarts, and you get them to sit down and agree to work for the public, in the public eye, and to say what they can agree on, what they can't agree on, what is solid, what is speculative, what is silly, usually on the scientist's nickel, usually not the government's. And this has been going on. The National Academy of Sciences is still the main advisor to the U.S. government. The IPCC is a UN creature that is doing the same thing for the world for climate change, which is get the full range of views, get the scientists, get people to sit down with the public watching, with the public commenting, with the policymakers insisting that they be able to understand the words when they come out and that it not be in scientific ease, and then to say what can the science support, what does the science not support. And it's amazing. You know, thousands of people have been involved. We were most recently writing the 4th assessment report. So this has gone on 4 times at 5 to 6 year intervals. There's 3 working groups. What's the science? What does it mean to living things, including us? How can we put up with it? And what might we do to head it off? We had 11 chapters in the first of the working groups. We wrote 4 drafts of the things. The first draft, well, the 0th order, the first order draft, we had over 1,000 public comments on, and we wrote a document in which we responded to each one and explained either why we changed it because they were right or why that was not consistent with the underlying science.
And you've been criticized from both ends.
Oh, absolutely.
You've been criticized by those still arguing and skeptics, the naysayers, as well as those who say you're not going far enough in what you're recommending and what you're suggesting might happen.
Oh, very clearly. And in fact, the IPCC does not recommend. We simply assess the science. The policymakers who ask that this happen reserve to themselves the right to decide what laws will be made, what options will be done. We try to show, first of all, what does the science show, what doesn't it show, and then by the time you get to the what are the options, can we put up with this, can we change how we make energy, they try to show options, but they never pick one and say this is what you should do. The IPCC is not, as we say, policy prescriptive. It will never tell you what to do. It will only tell you what the science supports as possibilities that you might do.
I want to talk about the continuing arguing that you mentioned and the naysayers and skeptics, but I wanted to first talk about the fact that you are one of the best known science communicators out there today, and I think it's fair to say that twice weekly we might see you on NPR or the BBC or Nova, the New York Times. Do you feel like that's part of your responsibility to do that kind of communicating?
Oh, absolutely. We are not the most expensive thing in the world. If you take science as a fraction of the whole economy, it's pretty small, but we're still expensive. And climate science, you know, when in the 70s when we said we need a good climate science, one of the things was we've got to observe the world. We have to see what's going on, and that means satellites. And satellites, you know, $300 million for a satellite, it doesn't take long until you're into real money. And so people really have paid for us to do things. We owe it to them. We are talking about changes that are going to involve all of us. The sort of central estimates are that we could change the energy structure in a way that generates all the good things that we now get from energy use without changing the atmosphere for a cost which is vaguely 1% of the world economy. And we could spin that in many ways, because 1% of the world economy is $600 billion a year or something like that. So I can say, oh, it's just 1%, don't worry. And I can say, $600 billion a year, are you out of your mind? So, and it's the same thing, exactly. But that will require remaking a few percent of the world economy. Now you go and fill up the gas tank. In the future, will you fill up the hydrogen tank? Will you get the bicycle? Will you telecommute? Will you be using ethanol from sawdust? It will be something that's different. And so what we do and how we do it is likely to change. Eventually we run out of oil. There's just no question that eventually this has to change.
Now, you mentioned do we telecommute, and you do that. You sort of walk the talk. You live in a modest ranch house in State College, Pennsylvania, for the most part, except kids are off to school. You have one car. You either run or ride your bicycle to work every day. Is this an effort to reduce your personal footprint? And the reason I ask that is I've heard scientists who are naysayers say, if people really believe this, they would change wholesale the way they live. And it seems to me you've done that.
Some of that I've done, and that is one of the reasons. And I do believe that personally, I want to be consistent. I don't want to tell people to do one thing and do something else. But the sort of, oh, look, he got on the plane to go to the scientific meeting, so he doesn't believe, so he's a bad person, is not right, and I don't think it's fair. If all of us who realize that there's an issue, if all of us who realize that by changing human behavior we can make ourselves and our grandchildren happier and healthier, if the moment we realized that, we stayed at home and shut up, and we didn't tell anyone, and we didn't get on the plane, and we didn't do the research, and we didn't talk to the Senate, and we didn't do all those things, who would know, right? The moment anyone realizes, they shut up. And that clearly won't work. And it's the analogy, you know, if you're going to try to jump the canyon on your bicycle, and you got to hit the ramp fast. And there are times that you say, look, I know in getting on the plane to go to the meeting that I'm making it a little bit worse. But if I stay home, will it get better? And I'm virtually certain it won't. So on a personal level, I try to do what I can, but I will get on the plane and go to the meeting because I think it's a responsibility.
How do you balance the research with the outreach?
I'll lose my mind. Fortunately, what we have here at Penn State now is that there's quite a number of people who work in the same general area that I do who are really, really good. And if you were to come by to our ICE group meeting, we buy pizza on Fridays and see what's going on. And we've got Sridhar, and we've got Dave, and we've got Todd, and we've got Byron, and these people are all world class. And so right now there is so much good stuff going on here that I personally can be useless, and still the science goes forward.
You've won a number of teaching awards, and it's no surprise your enthusiasm is infectious. And I'm wondering, after all of these years, how do you maintain the enthusiasm for teaching?
Yeah, well, it's still fun. There are still things to be done, and clearly, there's days that some student says, but I just got to get the grade, and you say, oh, but they do. They need the grade to get their scholarship or what have you. And there's days the student comes in and says, this is really cool. What else can I do? So people are still bright. There's still good things coming. They're still having fun, and so it's our fault if we're not enthusiastic.
No, you mentioned a moment ago satellites, and I said I was going to get back to the naysayers and the skeptics, and there's one in particular that I can think of, John Christie from the University of Alabama, a climatologist who says we're worrying about nothing when it comes to global warming. He has looked at the satellite records and he sees no warming trend. We're talking about a credentialed, respected scientist. How do you...
Yeah. Well, John's an interesting fellow. He tried to do something which is really hard. Back up a little bit. We have weather satellites. And weather cares about is today different from yesterday, but it doesn't care a huge amount about whether 30 years ago is different from now. And so the sort of very careful calibrations we're not done for the weather satellites. And John said, can we stitch these weather satellite records together and make a climate history? And it was a hard thing. And initially, he came up with no warming. And later, he and other groups went back, and they said, no, actually, there is warming. And in fact, his records now very clearly show warming in the mid-troposphere that matches warming at the surface. And the other groups show a little more warming than John does. But in fact, he has come around and said there is warming. Now, he has served on some of these assessments and other things. I think he helped the American Geophysical Union on their statement that says, yeah, it looks like we're changing the world. In the level of concern, I think he would focus on other places. And if he and I sat down over a beer and said, so where should we put our money, we'd probably come up with different answers. But he's a real scientist, and his real science does show a warming world now.
There are other scientists too, so this is, I think, part of what is confusing to the public. You've got the American Physical Society. I should mention that you're a member of the American Geophysical Union, which I think they're somehow related. But the American Physical Society, which represents some 50,000 physicists, a number of members who say that they don't believe humans are the primary cause of climate change. Then there's the Heartland Institute, which is a Chicago-based think tank that is attended by over 200 scientists and climatologists who also say we're worrying about nothing.
Yeah, there clearly is a spectrum from serious scientists who are on the edge of the field, who would disagree with aspects of the science, on to people who are essentially paid mouthpieces. And those clearly all exist in every possible gradation in between. The first thing is to be very careful about what they say. If we were to get people to sit down and say, okay, are we burning a lot of fossil fuels and adding CO2 to the atmosphere? You could probably find someone who's not in touch with reality who would argue, but nobody else would. Is CO2 a greenhouse gas? You could probably find 2 or 3 people who are not totally in touch with reality, but no one else would. Are we warming the climate? Even most of the prominent skeptics would say, yeah, we are. Is this a big deal? Should we panic? Is this a catastrophe? Is this a problem that's for the future or for today? And what happens is that people will say, oh, you global warmers want black helicopters to land at our gas station and keep us from getting gas. And the other side says, so there's people that are talking past each other because they won't take the time to find out what they agree on and what they don't agree on. The basic picture, we are changing the composition of the atmosphere. This is changing climate. The changes we've made are very small compared to the changes that are coming, and these will impact the living things. There's pretty much no credible disagreement with that. A little bit, but not much. This is a panic that we've got to do something about instantly. Now, that's one that we can talk about. Economically, Most economists would say that given what we know about the science, we should start investing now to head off the changes. But they would also say we should invest a little bit now. And we should take the rest of the money and invest it in making our grandchildren really, really rich. And our rich grandchildren will solve the problem rather than us poor people solving the problem. And so the economic story is you put a little money into heading off global warming, you put a lot of money into getting rich, and then rich people are supposed to solve the problem in the future.
In fact, you do a talk. One of the 3 talks you're doing currently is Get Rich, Save the Planet.
Absolutely, because and it does, the economist says, we just want to make the economy big. And in fact, the way to make the economy big does involve investing now in heading off global warming. You say not hugely. The ethicist says, no, wait a minute. Says there's more than just the economy in the world, because right now, most of the people are not economically very important. Somebody who makes $300 a year and you make $30,000 a year, and does that make you 100 times more important? Well, in an economic model, there's a difference here. And right now, the economy is not being hurt much by global warming, but many people are. And so an ethicist is going to say, no, you got to do more than just optimize the economy here, because there is an issue of fairness here. And they'll also say, and is it fair to just dump the changed world, the endangered species and what have you on your grandchildren's grandchildren and say, you're wealthy, you fix it. And so there's really, really big ethical issues that come through. But ultimately, these are where the discussion lives. The basic discussion, are we changing the climate? The scientific confidence that we are is higher than the scientific confidence that underlies a whole lot of things that Congress passes laws on.
And I just mentioned a moment ago that 41% of the American public says the threat is overstated. So we've got a little bit of a problem, a little bit of a disconnect there. And you say that we need to spend the next 20 years convincing the public that the problem is here. And I wonder, 20 years sounds like a long time.
Yeah, I've been Penn State 21, and I'm going to work another 21, so we can work on it. It is a long time, but it's, you know, if you want to turn a big ship, you start getting on the tiller way before you got to miss the rock up there. And our energy, our economy is a big ship.
Well, to what extent is, you know, we've got the greenies, I guess, on one side, and naysayers and the politics involved in all of this on one side. But there is this growing notion that the science is right, but there is also this element of, well, it might be right, but we're too far gone.
Yeah, I don't believe that one. We clearly have committed ourselves to changes. And if we were to stabilize the atmosphere right now so that we're not changing CO2 at all in the atmosphere, we will see a little more warming. We will see a little more melting of some glaciers. We'll see biology shift some more. When you come into a cold room and turn on the heater in the winter, you have to warm the furniture before the air gets up to full warmth. And we are warming the furniture, we're warming the rocks and the ocean especially. And so we're committed to a little more change. But the change so far, we're here. You know, we haven't killed ourselves off. We haven't killed off all the species yet. And the change that we're committed to is not big enough to destroy humanity. You know, we're going to be here. And there's a lot of room to make changes, to reduce the impact that we have, and to find newer and better ways to do it.
A growing number of scientists have criticized the media because they say that they've exacerbated this problem, this disconnect with the public, in the name of journalistic balance, providing equal time to global warming skeptics. What's interesting to me is that we're all on different agendas, different timelines. The scientist is in it for the long haul, looking, you know, doing their work. You've got the politician who's looking at a timeline that might be their term, 2 years or 4 years or what have you. And of course the media, which is 24/7 and turning a quick story. So I'm just wondering, as someone who is known as a communicator and bringing the science to the media, what's the answer to this?
Yeah, I don't. It's hard. I do believe that there has been a bit of false balance. There's a lot of stories that say, well, the National Academy of Sciences says this, but this individual disagrees. And no, those are not equivalent by any means. It's the most optimistic way to view it is that we'll find win-win situations down the way. That we will find ways that, as these researchers over here are looking for ways to make energy without changing the atmosphere, they're looking for new ways to make energy that will actually leapfrog into a situation that's better for everyone. And we'll look at those fossil fuels and say, just leave them there because we don't want them. We got better ways. It's certain. We enjoy what we get from energy. You know, it's really nice that we can fly if we need to, and it's, you know, I like to say, if I were to keel over here right now, you would have an ambulance out here from the hospital in about no time. You'd have a machine that's breathing for me. You'd save me, and you'd use energy to do it. We like this. There are a lot of people in the world that are never going to outbid us for the oil and the coal because they don't have the money. They can't get the good things we get from this energy because it's too expensive because we've paid so much for it and raised the price. They will be happy if we can do this by sun, if we can do this by wind, if we can find a way to get them the energy that, the good things that we get from the energy at a lower price. Doing what we're doing more and more and more doesn't look like it's going to do that. I don't see any way that sniffing around for more oil is actually going to bring the price down, that somebody who makes $300 a year is going to be able to afford what we have.
You say there may be better ways, and many think that one of those better ways is nuclear power. And I'm wondering what your take is on that.
Yeah, that one's one of the toughest ones. It is very clear that nuclear makes a good chunk of electricity. We're using it here. France is using it a whole lot. It has costs. The mining is not perfectly clean, but we know how to do it better than we used to. It's going to be expensive. New plants are looking like you have to put billions of dollars up front before you can bring a plant online. So if you're a really poor person in a really poor country, that's not going to be an easy answer in the very near future. If the United States, we may see nukes being built. My suspicion is that it will figure in the bridge to the future and it won't be a dominant player, but that's just sort of a wild guess. And it's based on, first of all, it's hard to imagine sort of the stable situation and the investment being available in some countries that you'd want to make nuclear there and that you'd be confident that you could do it for a long period of times and that the nuclear waste would not fall in the wrong hands or something like that. We in this country have had difficulty agreeing on what to do with the waste. We know things that can be done, but we haven't agreed on one yet. And so it's just sort of piling up at the plants, and eventually one suspects that there will have to be something done with that, and our political difficulty in dealing with that says that this one's not going to be easy in the future. And so my gut feeling is that it matters as a bridge. It's good that we have a nuclear engineering department here. There are going to be needs for the graduates in the future. But my guess is that we won't solve our way out of this primarily by nuclear.
Well, here's one solution that's being presented by Wallace Broker from Columbia University, an oceanographer there, who says what we need are these big machines that will take the CO2 and pump it into the ground and turn them into carbon-rich rocks. And while he says that won't be cheap, it certainly will be easier than the social engineering that would be required to change our lifestyles.
Right. Yeah. Wally Broker is an amazingly good scientist. He's a friend now too, but he's been doing wonderful things for a very long time. Do not discount him, okay? Ever. He's really amazing. It's for decades at least. The cost of doing that is sort of the same as this 1% of the world economy. You could take the CO2 and you could put it in the ground. It's very clear that we know how to put CO2 in the ground because
keep it there?
For some period, yes. It is being done and it is staying for now. People are using it to get oil out because, you know, if you take a snow cone and you put a straw in and suck, and after a while there's still pink in there when you sort of have troubles getting more out. And the same way you drill a hole and you try to get the oil out, there's still oil out in those cracks. And in your snow cone, if you were to add a little water, you could sort of float some of the pink out and pull it away. What they're doing is they're adding CO2 and they're forcing the oil through to the wells. And it's just clearly going on. People are clearly putting CO2 down there and they're using it to get oil out economically. If you put the CO2 down and didn't pull the oil out, or you put the CO2 down and after the oil is all pulled out, put some more CO2 down, you're just putting it down.
Let's get back to your love, which is the polar ice sheets, and in particular the West Antarctic ice sheet, which seems to be of particular interest. Tell us what's happening with them and how concerned are you?
Yeah, so these ice sheets are 2-mile thick continent-wide piles, and that's water that's not in the ocean. And if we were to melt Greenland, you get about 23 feet vertically averaged over the world's ocean. West Antarctica is maybe 18 or 20, something in there. East Antarctica is a lot more. The ice sheets so far are putting a little water into the ocean. Sea level has been rising something, 3 millimeters a year or so. So that's a little over an inch a decade. And if you live at the top of a cliff of granite, you don't care, and if you live in North Dakota, you don't care, and if you live on a really gradually sloping beach, you know that your beach is coming back at you, and most of the coastline is retreating from that little bit of sea level rise. Of that sea level rise, some of it the ocean's warming and is getting bigger, some of it the mountain glaciers are melting, and a little of it is coming from the ice sheets. We've warmed a little, the ice sheets are melting a little, and the concern is if we warm a lot more, will the ice sheets melt a lot more? And everything that we're seeing now points in that direction, that as we turn the temperature up, that the ice will melt around the edges and it will flow faster and dump more icebergs out, and that'll raise sea level. And whether there's a tipping point there that we're close to is maybe the biggest thing that we're working on now in our big research group here at Penn State, and others are working on, because it is clear that there can be tipping points for ice sheets, that you push them a little too far and now they're not going to recover without huge help. And they might, we don't think you can dump an ice sheet in decades. We think it would take at least centuries to put a whole ice sheet into the ocean and get 20 or 40 or 60 feet of sea level rise. But we might, within decades, commit ourselves to that. And you get to the point that
with no turning back.
With no turning back, or without, if we put a giant shield up and blocked the sun in space and made it real cold, you could turn back, but it gets really hard to turn back.
Now, you and your colleagues are working really on research that helps to determine how the world works, and you say you've discovered some interesting things. You're working soon on publishing this. Can you give us kind of a sneak preview of some of the things you've found and are most exciting to you?
We, especially Sridhar Nandakrishnan over, he's this amazing exploration geophysicist, and he goes out and he figures out what's in and under the ice with his students, and they come back, and every time they come back they found something that we didn't know. And so the most recent one is just about to come out about there's lakes under the ice sheet, and the lakes have outbursts, and you can hear them tunneling their way under the ice from one place to the next. And this will be moving water, it'll be changing the lubrication and the flow of the ice, and so it's one of these things we didn't have in our models of the ice sheets, that these things are tunneling their ways through. We were interested in Greenland. There are these beautiful lakes that sit on top of the ice, and then the lakes drain to the bottom, and then the ice gets floated off and it goes faster. And so we're trying to figure out how is it that these work, and a bunch of us built a model and said, this is what's going to happen. You're going to find that these big lakes form, and then that they open crevasses, and they dump down these crevasses really, really fast, and that's the way the water gets to the bottom, and that we'll have to understand the crevassing to predict the future. And then a former PhD student here, Sarah Das, and a colleague of hers, Ian Jochen, went up to Greenland, and they camped next to the lakes, and they put out sensors, and they went around in their boats on the lakes and what have you. And one day the lake opened a giant crevasse, and it was doing Niagara Falls plus for an hour into the ice, and it did exactly what we said it would. So there's a process that we're going to have to put in the models, and there's a bunch more of these. And so far, every time that the field people come back, they say, wow, we found something that we didn't know before. And unfortunately, what that means is we can't predict the ice sheet yet, because we're going to have to understand all the pieces that matter and put them in our computer before we can predict the future. We've got people, Byron Parasek, Dave Pollard, Dave Hocko, some other people who are working really hard to put it in. As soon as this new stuff comes back, they put it in the model. And so we're pushing ahead hard to be able to predict the future, but nature still has things. We haven't lifted all the lids yet.
Well, some say, speaking of the future, some say that the problem when it comes to global warming is not a lack of scientific information, or even a lack of disseminating that information, but really a failure to be changed by what we learn. And I'm wondering, based on that, what kind of a future do you see? And what advice would you give to the American public on this whole subject?
Right. The most optimistic, the best one, is that the American public should send their smart kids here, or other schools, and they should make sure that some of them are interested in inventing our way to the future. You know, we really do need people who worry about getting along with people. And 10% of the problem is going to be technical, and 90% is going to be people, because that's always the way the world works. But we're going to need a few more of the technical folks who are going to build the solar cells, who are going to figure out the engineering and the science of this. And so we really need to see bright science, math, physics, chemistry, biology, engineers, scientists coming in to help us. And we need to be able to tell those students, your country is behind you, and we're going to work really hard to make sure that you have a job if you actually spend 4 years doing differential equations, okay? Because you don't want to tell people you have to bust your butt and then you're going to be unemployed when you get out. So in terms of the easiest way to the future that I see is to convince these very bright young people that most of them are still going to worry about getting along with the other people and making the economy run, but a few of them should be coming over to us in the technical side and inventing the future. And if we do that, we're going to be a lot of the way there. Then you want to help to make sure that the things that they've invented can move out into the real world. And that means making sure that if you're damaging somebody else, that you pay for it.
Richard Alley, it's been a pleasure talking with you.
Patty, thank you so much.
I hope you've enjoyed our conversation with Richard Alley, Evan Pugh Professor of Geosciences at Penn State. To see more of Alley's music videos, a mix of rock and roll with scientific lessons, visit our website at conversations.psu.edu. We look forward to seeing you for our next conversation from Penn State.
Production funding provided in part by the Corporation for Public Broadcasting and by viewers like you. Thank you. This has been a production of WPSU. A copy of the program you've just seen can be purchased through Penn State Media Sales at mediasales.psu.edu or by calling 800-770-2111.